Hello, everyone, and welcome to our live session. It's been a few weeks. We are happy to be back with you. My name is Matthew. I am one of the instructors for our online classes, and I'm going to let Professor Impey take over and welcome you all, and then we'll get started with your questions. Please post those in the chat.
Okay, hello everyone. After a few weeks break, we're here for anyone who takes one of our online classes or who's just heard about these sessions and wants to participate. So I'm happy to take questions on any topic in astronomy.
Excellent. There seems to be a little buzzing. I apologize for that if it's coming through to everyone. We're going to try and troubleshoot that for next time. But the first question is from Dimitris Siropoulos, who's on with us live. In the transit method, how do scientists distinguish the dimming of solar radiation and whether it's due to the planet transit and not due to solar activity itself, as in fluctuations of solar radiation?
Right. So luckily, the transit method for exoplanet detection depends on repeated observations. So once you have a transit, exoplanet transit, you know that it's going to repeat with the orbital period. And so you just gather more data. In fact, you don't confirm the transit until the third transit is detected. Weather, star weather, fluctuations in stellar brightness and so on, which can be significant, they have no such regularity. So that's the real way to distinguish them. So with a single transit or a single observation, you couldn't be sure. But because you always have repeated observations, then you can always separate these two.
Excellent. The next question is from an email. Wendy Traver asks, is it possible that we should be studying the sun more closely to look for reasons that the Earth harbors life rather than looking for liquid water or distance from a star or that kind of thing?
Well, the nature of the star does affect the life on any planet, of course. So we imagine a sun-like star, a mid-range star, G-type star in our case, is a typical host star for a planet with life, but that doesn't have to be the case. It may actually not be the best kind of star. So we do need to know more about the details of our star, because obviously there's extreme space weather caused by solar flares and super flares, and those super flares can be really harmful to life on a planet. They can blast away the ozone layer, lead to enormous mutation rates, spiking mutation rates due to cosmic rays and high energy particles. So the nature of a star's activity is really important to the way life can survive and persist and endure on a planet. And so yes, we do need to study the sun and know about it in more detail. We don't imagine that it's the best of all possible host stars for life. It is probably not the worst either.
So the buzzing is actually fairly bad. I just listened to the YouTube stream. Can you just maybe stretch out the microphone cable so it's not overlapping on itself and see if that helps a little bit? Sometimes there's a little bit of feedback in there.
Yeah, it's kind of tangled.
Okay, yeah.
Right
That
on.
already sounds better. I'm going to listen to the stream and just make sure.
Okay.
Okay, so the next question is from one of our, let's see, live participants, from Lawrence K. Regarding the uncertainty principle, is it correct to say that the principle is not an observer effect? That is, not a limitation on the ability to measure, but a limitation of reality?
Yes, that's fair to say, because the principle relates to physical quantities. So the uncertainty principle, whether it's the form that involves momentum or position or the equivalent form that involves energy and time, it doesn't refer to the nature of an observation or any observation at all. So it is implied to be a fundamental floor to the knowledge we can have of nature. And then when we make an observation, we have limitations of the observation itself, and they fold into that. But basically, what the uncertainty principle is saying is that regardless of the quality of our measurement, there is a floor to the ability to measure precision of physical quantities in the universe.
The next question is from Hernan Reyes, who sent an email. Much has been said about the Miller-Urey experiment. I recently read that in 2009, a PhD student at the University of Arizona, one Sarah Horst, worked on a new Miller-Urey experiment, this time creating the conditions as we suppose them to be on Titan. Can you talk about that experiment? Are you familiar with it? It says, anyway, you can talk a little bit about it, and there's some follow-ups based on what you say.
Yeah, Sarah Horst was a graduate student over in planetary sciences across the street from us, and she was one of their star grad students and has gone on to be a rising star in astrobiology. She has a faculty position on the East Coast, I'm not sure which university. So she's doing very well. And in this work, they simulated what might happen in the upper Titan atmosphere, and in particular, what kind of biochemical precursor interactions might happen given the ingredients there. And intriguingly, a number of amino acids and sort of prototypical building blocks of life could be produced naturally in the atmosphere of Titan. There was an interesting trade-off, however. In their model, they had a small amount of oxygen, and that small amount of oxygen was actually necessary to facilitate some of the reactions. Without any oxygen, it's likely that many of these complex compounds would not have occurred. And with too much oxygen, essentially the atmosphere would have partially combusted, and so you wouldn't have got these products. So there was a balancing act there in the conditions they set up. But the end point of it was to deduce that there is definitely a plausible biochemical backdrop in the atmosphere of Titan that could lead you to imagine an alternative form of life there.
And then the sort of follow-up question to that is, so it didn't create life, correct? It just created these amino acids. So can you talk a little bit about whether that's related to, or how it's related to this concept of Hachimoji DNA? So there's this, the synthetic DNA. Is this sort of just theoretical and interesting, or do you think it opens the way towards understanding more about life 2.0?
So there's a large field. So this question is really about synthetic biology. So let me talk briefly about that. Synthetic biology is a field of biology that's been active for a couple of decades now and is benefiting enormously from the genomic advances of the last decade, the ease of doing genetic sequences, the ease of manipulating genetic material, and the ability to do quite sophisticated experiments in the lab on genetic material. The Hashimoto result from a few years ago by a Japanese research group, Hachi is the Japanese for 8, so this actually involved 8 bases. So the nucleotide basis of the life on Earth is based on 4 and then an added 5th. And in this experiment, they synthetically created another 3 bases to end up with 8 nucleotides. And then they watched these interactions and the development of more complex molecules in that mixture. And they deduced that by increasing the toolkit, the sort of basic toolkit of life, they doubled the complexity and the information capacity of the genetic material that they were working with. So this is a very exciting genetic experiment that is literally altering the base blueprint of life by adding in new components that were created synthetically. Once created, they could interact with other ingredients in the mixture and then produce other interactions. Now it's important, since some people get a Frankenstein DNA thing going on when they hear about these stories, it's important that the researchers noted that the mixture they created, the Hashimoto DNA and RNA, they could not survive outside the lab. If for some reason this mixture escaped or went out into the world, it would become inert very quickly. So it's not a self-sustaining biological system by any means. However, to answer the end of the question, it is an important demonstration that we can alter the toolkit of life, and therefore enabling us to wonder how variations of this toolkit may have played out in different parts of the universe. Because there's no suggestion by any biochemist that the genetic blueprint or the genetic code is optimal or perfect or the only possible genetic code. In a sense, life does just good enough. It's just good enough. It has just enough error checking, just enough redundancy, just enough energy usage and information storage to do the job efficiently. But it doesn't have to be optimized. And so there's plenty of space for exploration.
Excellent. Thank you very much. The next question is from David Gold, who's on with us live. In light of the universe expanding at an accelerating rate, what is the expected impact to the universe's relative percentage of matter, and dark energy in the distant future?
Well, the projection of the current accelerating universe is that in the distant future, it isn't even that distant, a few billion years from now, the fraction of dark energy in the universe, which is currently about 2/3, with about just under 1/3 dark matter and then 5% normal baryonic material, the stuff we're made of, and all stars and galaxies. That ratio is going to change dramatically in the direction of dark energy, because of course the dark matter and the normal matter, the stuff we're made of, will be diluted rapidly in the accelerating, expanding space. And so the universe will be dark energy dominated at the level of 99 and then 99.99% in the few billion years in the future. And that's essentially how the universe will stay. There's no countervailing force that will change that situation.
The next question is from one of our live participants. Tony asks, this is a philosophical and scientific question. Is Nietzsche's eternal recurrence physically possible? When the universe ends, I hear there's a chance it'll eventually come back into existence. Does that include me and this life?
There's a part of astronomy that connects with anthropology and cultural history. In societies around the world, there's been something called the myth of the eternal return. And Nietzsche knew about this. This idea goes back hundreds of years in scholarship and goes in human cultures back thousands of years across the world. So it's a very common idea in human history that humans are destined to have their time on Earth and will eventually not persist, and that eventually there'll be a return. Now, there's no reason for biology to expect this will happen in biology. And there's also no reason in cosmology to expect this will happen either. So the eternal return idea, the idea that humans once extinguished will eventually recur, is an idea that doesn't really have a basis in science. It's more of a cultural idea. It may be reassuring to think that we can exist and persist and reoccur and not be gone from the universe, but physics doesn't offer much solace.
The next question is from Beautiful Crime. Does someone know, or can you talk about how to start writing articles for journals for a high school student? Do you know if there are any journals that are potentially student friendly? How does one get started with something like that?
So I think I took the question to be writing high school students writing articles or writing articles for high school students. I missed the sense of the question.
I think it's high school students writing articles to be published.
Right. So if you're in high school and you're interested in astronomy and know about it and think you might want to have articles published, the simplest way to get started, of course, is to put up a blog, because that's very easy. It doesn't even have to cost any money, and you can get your friends, colleagues, and peers to comment on it, and you can refine and hone your writing skills. And once you have a persistent presence online and have had people comment on your work and give you feedback, then you're probably well set up to try and put your work in small venues. Of course, science writing is tricky now because the number of venues for science writing has gone down. The number of science journalists has declined. The number of newspapers with science sections has diminished. So more you're talking about online places where you might put articles. As for places that will take high school students' work, I mean, as long as this work is well sourced and referenced, nobody's going to discriminate against a high school student, a smart high school student who knows their stuff and has documented what they write. So I wouldn't let the fact that you're in high school deter you from that. And not coming up with any obvious venues for this, because it's really hard. It's a hard business now. There's not too many out there. But getting noticed and just researching the blogosphere for the more professionally produced blogs that take new science writers, and that may be a way to come on board, to be a junior writer for one of the well-known science blogs that bundle a lot of science content. And then you start getting noticed by other people and other journals because they get a large viewership.
So the next question is from one of our live participants, P51, who has a follow-up to the earlier discussion about stars dimming. And this has been in the news recently. They ask, what if a star ejects a big quantity of dust, like Betelgeuse? Can you talk a little bit about how that affects the dimming and maybe some of the recent results and kind of discussion about how we found out what was happening when Betelgeuse was dimming?
So a lot of stars of various kinds and various masses lose mass late in their lives. The sun will do so. The sun will go through a planetary nebula phase and will eject an envelope of gas and dust before it goes to red giant phase and then white dwarf. So many stars do what Betelgeuse does. Betelgeuse is a red supergiant, however. It's much more massive and has a much more dramatic loss of its envelope. And it's a cooler star, and the coolness actually facilitates the creation of dust grains. So it's the cool supergiants that tend to have the most dusty outer envelopes and where the presence of dust is most significant. And so that means, as seen from afar, that dust is an obscuring effect, and so they appear to dim quite dramatically sometimes. A very small amount of dust can create a large amount of dimming. So astronomers actually have to know the model of the star and its behavior very well to predict the dimming that might come from dust. And unfortunately, the theory and the observations are just not good enough to make that prediction. So we're not in a position to say for a particular star what dimming we should expect due to dust in its outer atmosphere.
The next question is from Frank Allen. Should we on Earth be concerned with rogue black holes moving in our galaxy?
I don't think so. The number of black holes in the galaxy is roughly 30 million. That sounds like a lot, but it's a big galaxy. And the distance to the nearest black holes is of order 1,000 light years. So black holes are free from other stars, and so dark objects floating through interstellar space. The vastness of interstellar space almost guarantees that they're unlikely to ever encounter anything in billions of years. So you can do the statistics on it, and the statistics are an encounter with a rogue black hole is an extraordinarily unlikely event.
Uh, Eva Bekesi would like to know, can anyone file a research proposal for a ground-based or space telescope if it meets the scientific criteria?
It's an interesting question because the different places where you can apply for time have different rules. So I can't give a general answer because there is no general answer. For example, Hubble Space Telescope has famously had a small category of proposals every cycle, which can go to people who don't have a professional astronomical affiliation. So that it will include amateur astronomers, high school teachers, just citizen scientists essentially, and they give time every year for that. Now, some of the major observatories have copied that program, but typically they sequester off a pretty small percentage of time and they solicit proposals from non-professional astronomers, and they are subject to peer review, as all proposals are. And so the odds of getting that time are, not great. They're not great for a professional astronomer too. You have to pretty much go to each astronomer's site to see this. So you can go to the Peak or the Sarasolo National Observatories, north and south, or the Keck Observatory site, or the European Southern Observatory. I don't really know what their rules are. And they will all have a different mechanism for this. And some may not have a mechanism at all, I will admit. But many do, including Hubble.
Laurent CS asks, do you think it will be possible in our lifetime for humans to safely travel through a black hole?
I think not, because I don't think we'll be in a position to approach or do an experiment like that in our lifetimes, because the nearest black hole is so far away. So the odds of us being in a position to go through a black hole are very low. We'll have to do interstellar travel and have been doing it probably for hundreds of years before that's possible. So this is not an experiment that we can reasonably do in our lifetime, and in truth it may never happen because space is large, the distance to the nearest black hole is truly prodigious. Just getting to the nearest star is going to be a challenge for the next century, let alone getting to a black hole, which might be typically 100 times further away.
The next question is from Tom. If the universe is actually infinite in size, it must have been infinite in size at the time of the Big Bang. I'm not sure that logic follows, but apparently it must have been finite in size at the time of the Big Bang. If that is the case, how did the Big Bang occur everywhere at the exact same time?
Well, the speculation that the universe is infinite, that space-time is infinite, is speculation. It's not experimentally confirmed. The Big Bang does indeed posit a space-time event, the creation of space-time at one time, roughly 13.8 billion years ago, and in no particular location, of course, because it's the entire universe. And that space-time unfolds rapidly at first and then slower in a Hubble expansion. And so there doesn't have to be any particular location for this original event because all parts of the universe were once in one place. And then as far as what's beyond the things we can see, we're just limited by the time that light can travel in 13.8 billion years. So we can't comment on the universe being infinite or not because we can only see a distance corresponding to the amount of space light can travel through in 13.8 billion years.
The next question is from Anch, who's on with us live. How do we know that there is more matter than antimatter?
We know because matter and antimatter have well understood properties in quantum theory. Antimatter essentially has an opposite set of quantum numbers. That's obvious in terms of charge, where electric charge will be flipped. If it's positive, it goes negative. But it also applies to parity and spin and other quantum properties. And antimatter can be created routinely in the lab, so we know how to make it, and we know that it disappears instantly when it encounters matter. It's easy to detect antimatter in space because antimatter will come into the dominant form of matter and annihilate and create gamma rays. And we've had gamma ray telescopes and detectors for decades now, half a century. So if there were parts of the universe, parts of our galaxy, parts of the Milky Way, where there was a significant amount of antimatter, we'd see it, because anywhere there's an interface between antimatter and matter, you create annihilation radiation, very high energy radiation. And that's been ruled out for a very long time. So we've got very strong limits on the amount of antimatter in the universe. And it's a tiny, tiny fraction of a percent of the amount of matter.
And then as a follow-up question, is it possible that distant galaxies could be made entirely of antimatter?
So that becomes a little more plausible because intergalactic space is quite low density, but it's not zero density. We've learned in astronomy in the last few decades that intergalactic space is not totally empty. It actually consists of an extremely diffuse and very hot plasma that has a temperature of hundreds of thousands or even 1,000,000 degrees. And the only way we'd see it is it would be glowing in soft X-rays or hard ultraviolet radiation. But astronomers have shown that it exists. So there is a diffuse plasma between galaxies. And again, if an anti-galaxy existed, it would be surrounded by an antiplasma, but then the next galaxy would have a plasma around it, and anywhere there's an interface between the plasma and the antiplasma, you'd have annihilation radiation. So even if the galaxies themselves are well separated, the diffuse medium between them would betray the presence of antimatter.
All right, the next question is from Tawid Richardson, who asks, do scientists think that the Radcliffe wave in the Milky Way was caused by a dwarf galaxy? Or maybe the more general question is there any explanation for what has possibly caused this Radcliffe wave?
Right, so there are features in our galaxy. The Radcliffe wave is one, and there are others that have been found, which are generally called tidal streams. They represent the relics of an interaction of our galaxy with smaller galaxies over time that either fell into our galaxy or interacted with it and moved on. So they're sort of like fossilized remnants of a previous interaction. And they're very useful because you can do galactic archaeology with these features. You can figure out what galaxy our galaxy encountered, how many dwarf galaxies it might have encountered over its lifetime and swallowed to become larger, and so on. And we can also do some dark matter experiments with these interactions too. They're quite powerful.
Excellent. The next question is from Ad, who's on with us live, who would like to know, and I'll update it, how will or has commercial space exploration changed the field of astronomy?
Not yet, but it will. Commercial space exploration is now obviously a big thing. There were more commercial space launches to orbit last year, 2021, than government launches, and more space launches to orbit than any year in the history of space since Sputnik. So commercial space has taken off, literally and metaphorically. Most of these flights, of course, are for commercial purposes. So there's obviously a huge business involving the launching of satellites for telecommunication and Earth observing and monitoring the climate and so on. So that's the core business of commercial space enterprises. SpaceX obviously has made a sideline in ferrying supplies to the International Space Station at a time when the shuttle was grounded and the United States could not resupply the space station or get American astronauts into orbit. So SpaceX is doing that. None of the major space players, Blue Origin's, SpaceX, or Virgin Galactic, to put the third one in there, have any particular scientific aspirations, and they're not talking about launching telescopes or scientific missions. But as they find their feet and as they establish their economic model and start to return their investment to their shareholders, then that may change.
The next question is from Yash Palwi, who asks, does the failure of recent experiments regarding dark matter mean that we should take another look at our gravitational theory, or should we continue to look for dark matter?
It's a good question. Dark matter lab experiments, high-energy physics experiments, have not succeeded in measuring a dark matter particle. And this failure is starting to become more than inconvenient. It's starting to rule out some of the best candidates we had and the best mass and energy ranges we thought the dark matter particle might reside, if it is one particle. So these failures, I wouldn't say are fatal to the particle hypothesis for dark matter, but they certainly would mean that the people who all along have been studying alternative gravity theory should not stop that work. There's always been about 15 to 20 groups around the world doing research on alternative gravity theories, that is to say theories whose conceptual basis is quite different from general relativity. And that work will continue. It's a very difficult work, and at the moment no theory has come forward to supplant general relativity, but it's certainly a good idea to keep that work going.
So I don't know if a lot of our viewers know about it, but I thought that for those people who might have heard, we could talk briefly about Peak Observatory. Recently, it has been threatened by a fire. Can you talk a little bit about the sort of current state of that facility and
Sure.
what you know about the
Sure.
status?
Within the last week, a fire in the mountain ranges southwest of Tucson expanded. As I'm sure you know, the wildfire season in the western United States is bigger and stronger and earlier than ever before. This is really formally the beginning of summer. It's barely the beginning of the fire season. So this is called the Contreras fire. It grew very quickly. It had very tricky conditions, changing wind, and a lot of dry brush, no recent rain, and so firefighters, and very, very difficult terrain to work on. And as it swept up towards the observatory, it was making significant progress. So a pretty massive heroic effort that I think involved over 70 firefighters at once and several times. They were working in shifts because they were getting exhausted. We're making fire breaks, we're putting retardant on it, we're locking down buildings. The mountaintop has been evacuated for almost a week now. The fire, as I recall this morning, is just over 50% contained, so it's not. However, the observatory itself, the core buildings, the telescopes, are essentially out of harm's way. A couple of buildings were destroyed, and they were dorms, so there were no one was in the dorms. Everyone had been evacuated. So none of the scientific facilities have been impacted. However, a fire like this, which generates such heat and so much particulate matter, this particulate matter, smokes and bigger particles, will have impenetrated most of the buildings. And there's delicate scientific instruments that could not be removed from the telescopes or locked down or sealed. So there's a concern that some of the very sensitive scientific instruments, like the Dark Energy Survey telescope on the cubic 4 meter, might actually be affected and not able to start taking data for a couple of months while they deal with the consequence of essentially the smoke damage of the fire. So the worst seems to be over. It's mostly contained, and really enormous credit to the fire workers from all different states, not just Arizona, who got on top of it in the last few days.
Thank you very much, Chris. I appreciate that. Pashupati Nathdatta asks, can you please comment on regarding life on Mars? Maybe you can just talk generally about the status of for the search of life on Mars and the likelihood of finding it.
Yeah, the search for life on Mars is still some years away from fruition. Probably the best thing that's happening at the moment is the Perseverance rover is stashing samples, is drilling samples from a sedimentary formation where it landed, a lake bed, and is stashing them for eventual sample return to the Earth. But that's probably 8 or 9 years away. So that's a way of finding fossilized life on Mars in surface rocks from a possible location where there might have been active life a few billion years ago. Beyond that, it's hard to tell because the current rovers do not have the ability to dig deep under the subsoil where there might be liquid water or an aquifer. So none of the current experiments are really life detection experiments for real living life. Now it's been shown that there are places where there could well be life on Mars. There's research results just from this week, people working on a dry salt bed, a salt lake, very near the Arctic Circle, found microbes deep under the salt, so subterranean, that had a somewhat different biochemical basis from average Earth life. They didn't, for example, use oxygen as fuel or hydrogen as fuel. They used other chemicals as fuel. And these are models for Martian life forms. And the European ExoMars mission is going to use these microbes that were found as a test case of whether they could detect life. So true life detection on Mars is at least a decade away, basically.
The next question is from the 800 millimeter telescope project. Who's on with us live? Hello, Professor. What causes ripples and non-uniformity in the cosmic background radiation? Is it somehow related to the inflation after the Big Bang?
The features on the microwave background, the global feature that you can see when the map is shown at the right contrast and stretch, is a dipole moment representing the motion of the Milky Way and the galaxies around us relative to the larger mass of the universe. That's a motion of about 550 or 600 kilometers per second. So that's a dipole. Then when you take that out and you take out the galaxy signal, which concentrates towards the center, you do see ripples, fluctuations that are about 1 part in 10 to the 5 or 1,000th of a percent in temperature or brightness. And those are the seeds for galaxy formation. Those were the small inhomogeneities in radiation that turned into inhomogeneities in matter that eventually grew by slow gravitational contraction to form galaxies. And so that's what those ripples represent. And in the sense that inflation is correct, then the inflation theory predicts that those ripples were actually initially amplified from the scale of quantum fluctuations. But the jury is still out on whether that interpretation is correct.
The next question is from Ron LS, who is on live with us from Paris. I read that a mission to Uranus may take place in 2042, similar to Cassini. Do you have any information about it, and do you think this planet is an interesting target?
Yes, NASA is definitely considering this. This is a long look. The astronomers had their decadal survey, their 10-year survey of projects and priorities for legislative funding, for federal funding. The planetary scientists just a few months earlier had their decadal survey, and this Uranus mission was one of their top priorities for the next tier, the one after the current development phase. And that's a long time away. Uranus is, of course, a neglected planet because of all the missions, the Voyagers, Pioneers, spacecraft that were sent in the 70s and 80s that did approaches to the outer planets, the gas giants, Uranus only was visited by one of those spacecraft. So it's really only been looked at by one spacecraft decades ago. So it's the most unknown of the gas giant planets, and there's no reason that it won't be as interesting as any of the others. And it will have moons, of course, that could be very interesting and could potentially harbor life, because many moons of giant planets have liquid water under their surfaces. So it's obviously a good idea. It's expensive. It's probably a $3 to $4 billion mission, I'm sure, and it's a 20-year timeline. So you've got to have a lot of patience and fortitude to stick it out.
Mashon Adero asks, I'm interested in spheres and hexagons, where hexagons are more economical on material. If nature likes efficiency, are there other places where we get hexagonal shapes naturally as opposed to spheres besides beehives?
Yes, there are definitely. There are geological places. There are certainly many crystal formations where hexagons are preferred. But sometimes that's not an energy condition. Sometimes that's due to the bond valence angles of the individual molecules. So you have to be careful about that. I would say that the geological example I put forward, which is found in other places in the world, but the most striking example is Giant's Causeway in Northern Ireland. Giant's Causeway is a coastal basalt formation of sort of staggered steps, each in the shape of a hexagon. So these are hexagonal piles of rock with different levels, eroded to different levels. Each one is big enough to stand on. I've been there a few times. It's a spectacular place to visit. And that is just essentially caused by a minimum energy argument of cooling, rapidly heating and cooling magma, where it will preferentially form into a hexagonal shape for minimum energy reason. So that's the best example. But there are other examples in geology that lead to hexagons too, for the same reason.
P51, who's on with us live, is asking about particle accelerators and fusion generation. Is it possible that either of these kinds of facilities or structures could go into overdrive somehow and produce a black hole here on Earth?
No, the ability we have to compress matter, which is what you would need to do to create a black hole, and we can do that with lasers, and we can do that with particle accelerators. When you do the math, the most powerful terawatt lasers and the most powerful multi-GeV particle accelerators fall short by many orders of magnitude, 5, 6, 7 orders of magnitude, from creating instantaneous mass densities that would approach that of a black hole. So they just fall so far short of that. And no technology we're envisaging could do that either. So this is not a technology humans will have anytime soon.
Harry Bell, who's on with us live, asks, do the laws of physics regarding conservation of energy apply to the cosmic expansion of the universe?
Yes, the universe is bounded by a total energy principle. So as the universe expands, it has a certain amount of kinetic energy in the expansion, and it has a certain amount of gravitational potential energy from the gravity of the objects in the universe acting on each other. And that total amount of energy is constant. So a conservation of energy principle just applies to the expanding universe too, yes.
And then as a follow-up, will there be any energy or dark energy present at the heat death of the universe?
Well, if dark energy is the ubiquitous ingredient of the universe we think it is, and will eventually dominate the cosmic pie and the landscape because matter is so eventually diffuse, then dark energy will be the last remaining ingredient in the universe after matter is completely dissipated. It's not a form of energy that can be converted into anything because it has a negative pressure, has a very strange physical quality to it. So it's not energy that can be usefully used in any way.
The next question is from Richard Hull, who asks, how likely is it that fusion energy will become commercially viable or available?
Fusion has gone through a lot of changes, stops and starts, 50 years, disappointments, false promise, false dawns, and so on. Some even recently in the last few years. So the point of a sustainable fusion reaction where you get more energy out or as much energy out as you put into creating the fusion reaction, that has only been realized for a fraction of a second in any fusion facility. But it has been realized under a range of conditions and with the sense that other versions of these reactors could turn that sustainability from fraction of a second to longer, minutes, hours, years, and then you have a reactor, of course. But the energy cost of creating the reactor is substantial, and so it's not clear that this is ever going to be a better way to go than renewable energy sources.
Nashon Adero asks, can you please comment on any amazing prospects of quantum computing and the knowledge doubling curve for astronomical research? Should we prepare for accelerated timelines of breakthroughs?
Well, astronomy is surging along with the Moore's law progression, and the computation that a lot of astronomy depends on is fueled by computational advances, and these are mostly conventional computing. We've not reached the end of Moore's law, essentially. They're still with parallel processing and various other mechanisms, we're still able to squeeze more out of standard semiconductor-based computers. Quantum computers are in their infancy, and the most I've read of is something like 100 or a few hundred qubits of information. Those are quantum bits. So that's obviously a pretty paltry amount of digital information in a quantum computer. But the principles have been demonstrated, and so scaling that up is also just a matter of time and technology. But I think it's at least a decade before any quantum computer will be making a real impact on any scientific research problem.
Simon Rowland, who's on with us live, says, thank you for sparing your time today. Can you explain how liquid telescope mirrors work, and what, if any, future benefits are expected from developing this technique?
So the liquid mirror telescope idea has been around for decades, and the most common version of this is, of course, liquid mercury, because mercury is highly reflective metal, the only metal to be liquid at room temperature. And so if you put mercury in a cell and spin it up, it will take a parabolic surface. So you can have a transit telescope. These are not steerable telescopes, of course. And liquid mercury mirrors have been made in sizes 1 to, I think, ranging up to 3 meters. And there may be ideas for larger. And they're quite cheap, of course. Obviously, it's very easy to, if the mercury gets contaminated, you can replace it. It's a lot cheaper to make a mercury mirror telescope than a conventional telescope, although it's not as flexible because it can't point anywhere in the sky. So there's a niche for liquid mercury telescopes. And for people who think it's a dangerous thing to do, with appropriate monitoring of the conditions of the vapor pressure in the telescope dome, it's actually quite easy to keep the partial vapor pressure of the mercury low enough that it's not outgassing into the dome and getting people poisoned. So nobody that I know of, none of these telescopes that I know of have had problems with that.
All right, so it is 10:48. We have to leave a little early today, but we have time for 1 or 2 more questions. We'll see how long these take, but I just wanted to give everybody a heads up that we are ending just a little early today. Frank Allen asks, Professor, what is currently being done to avoid getting hit by asteroids that can cause mass extinctions on Earth?
What's currently being done is extensive monitoring of near-Earth objects, and that's very advanced now. So networks of telescopes around the world have cataloged all objects bigger than about 250 meters that are anywhere in space that could hit us. So those are the big ones that could cause a life-destroying event. So we know where they are. They're not going to surprise us. In the very unlikely event that one of them is on an Earth-crossing trajectory, we also have technology to deal with that. We can send a space probe out to the object ahead of time and either collide with it or just use the gravity of the space probe like a gravity tractor to slowly bend the angle or the vector of the incoming rock to miss the Earth. So there are strategies to save us, even if one of these was coming for us, odds of which are extremely unlikely.
All right, so this will be our final question for today. The alternate universe asks, do black hole binaries have irregular pulsar phases?
Well, black hole binaries are black holes orbiting each other, 2 black holes orbiting each other. So they're not pulsars, so they don't have the attribute of pulsars. They will, however, have radiation because they could well have acquired accretion disks earlier in their history or just from surrounding material. And so they definitely could have high energy radiation, accretion disks, X-ray emission, and pulses and so on. But they're not formally like pulsars, which are neutron stars rapidly rotating. Okay, thank you. Good questions, variety as always. And I don't remember if we have the next one on the books, but probably we do. And we'll let you know when it is. Thanks.
Yes, we currently don't have one scheduled, but we will be letting you know soon when the next ones are.
Right. And thanks to Matthew for facilitating. And we'll be back with you in a couple of weeks.
All right, take care, everyone. We'll turn on the post roll, and we hope you have a good rest of your week.